Hello everyone, I'm Binpeng Shi from Nankai University. Today I will present our work on a unified unsupervised framework for incident management in microservice systems to you. This is a collaborative work done by researchers from Nankai University, Microsoft, and Tsinghua University. In this presentation, we will work through the lifecycle of incident management in microservice systems and explain how we achieved unification across multiple tasks, including anomaly detection, failure triage, and root cause localization. We'll also cover the design of the ART framework and demonstrate its evaluation on two popular microservice systems. Microservice systems are now integral to many industries, providing essential services to millions of users daily. However, due to the dynamic and complex nature, incidents such as unplanned failures and outages are inevitable. As microservice systems grow in scale and complexity, these incidents, along with huge performance degradation, can severely impact user experience and lead to major economic loss. Therefore, it's vital to ensure the quality of microservice systems and manage incidents efficiently and effectively. Usually, a typical incident lifecycle involves four stages: anomaly detection, failure triage, root cause localization, and finally, incident mitigation. Each stage is time-consuming and labor-intensive. Currently, on-call engineers combine automated techniques for single tasks. However, this approach might introduce redundant efforts for multiple tasks, such as personalized feature extraction, offline model training configurations, and so on. OCEs call for an elegant and efficient unified modeling approach to incident management. Self-supervised learning offers a potential solution by extracting general representations from large-scale unlabeled data, which are then transferred to various tasks. However, applying SSL to incident management faces three challenges. First, the complexity of microservice systems data, making it hard to capture dependencies. Second, a lack of interpretability, making learned representations difficult to understand. Thirdly, limited label data, which hinders supervised fine-tuning for downstream tasks. To address the above challenges and design the model, we should figure out how to achieve the unification across multiple tasks. Our key question is, can we identify any commonalities among multiple tasks? And if so, how can we extract these commonalities effectively? In other words, does there exist any shared knowledge that we can leverage to achieve the unification in representation learning? With these research questions in mind, we lock our eyes on anomalous deviation, which is the difference between the prediction and observation. In our work, we define the two-level deviation at the instance and system level. Both of them are k-dimensional vectors, and each dimension represents the deviation of the instance or system from the expectations on the corresponding channel. In order to verify that the deviation is indicative for multiple tasks, we conducted an empirical study on the dataset generated from benchmark. We found that for anomaly detection, larger deviations at the system level helps identify an abnormal behavior. For failure triage, fluctuations on different data channels indicate different phenotypes. Lastly, root cause localization is achieved by analyzing the similarity between instance-level deviations and system-level deviations. We can conclude that deviations in the specific form of instance-level and system-level deviations contain shared knowledge about the microservice data, which forms the foundation of our framework. To effectively extract the shared knowledge, it's crucial to model microservice systems data accurately, leading to better prediction of normal patterns and precise deviation calculations. Our case study highlights the need to capture three dependencies in microservice systems. Firstly, channel dependencies, capture how different channels impact one another. Secondly, temporal dependencies capture the changes in data channels over time. Lastly, codependencies capture the interactions between different instances in the system. With this design motivation, we propose ART, a unified unsupervised framework for incident management. It consists of three models. Model 1, dependency-aware status learning. Model 2, unified linear representation acquisition. Model 3, unified unsupervised solutions for diagnostic tasks. The first model is responsible for modeling the complex data on microservice systems through a stepwise modeling of three dependencies. The first one, channel dependency. This is handled using a Transformer Encoder, which captures the relationships between different data channels. For instance, channels in disk I/O rate may correlate with changes in response time or CPU usage. ART treats each channel as a token in the input sequence for the transformer. Multi-head self-attention is applied to learn how channels influence one another by assigning attention weights, which allows ART to capture the correlations and mutual influence among different data channels from metrics, logs, and traces. The second one, temporal dependency. ART models how each channel's behavior fluctuates over time using a gated recurrent unit. Each GRU layer processes the time series data, leading to predict the next time step's behavior based on historic data. This temporal modeling helps capture patterns such as periodic spikes in CPU usage, which are crucial for predicting normal system status. The last one, codependency. Microservice instances often interact with each other, and the failure of one instance can propagate across the system. To model these interactions, ART construct a system behavior graph. The GraphSAGE is applied to this graph, aggregating information from neighboring nodes to learn how an instance status affects others. This captures cascading failure effects, ensuring that the model can understand both direct and indirect dependencies between services. The second model aims to obtain unified linear representations for multiple tasks by computing deviation matrices, which represent differences between predictions and observations. The ART model generates a deviation vector for each instance, indicating how it deviates from normal behavior across various dimensions. These individual deviations are then aggregated into a system-level deviation vector, offering a comprehensive view of system-wide deviations. Each dimension of the vectors corresponds to specific data channels, such as CPU usage, making it easier for engineers to identify and understand which resources or services are exhibiting abnormal behavior. The third model uses linear representations from Model 2. Specifically, ART monitors the L1 norm of the system-level deviation vector and uses an extreme value theory-based threshold from normal historic data to flag potential anomalies. Multiple flags within a short window confirm an incident, reducing false positives. Once detected, ART identifies the phenotype through country-based clustering, matching the new pheno's deviation to historical clusters. It then identifies the root cause by ranking instance-level deviations based on cosine similarity to system-level deviations. This model enables ART to perform unsupervised, real-time incident management, facilitating quick diagnosis and recover with minimal human effort. We evaluate ART on two popular microservice system datasets. Both of them replayed real-world business traffic and venues in microservice systems owned by top-tier global banks. we compared the performance of ART against several baselines in 3 tasks. The results show that ART consistently outperforms these existing methods across all tasks. These improvements are due to ART's ability to leverage shared knowledge across closely related tasks, using its dependency-aware modeling and unified linear representation. This slide addresses the efficiency of ART in terms of both training time and diagnosis time per incident. ART completes more tasks with fewer time because of its unified lightweight structure, which eliminates the need for task-specific models and reduces redundant efforts. In the ablation study, we explore how each component of ART contributes to the overall performance. We evaluate the effects of removing one of the 3 dependencies and test different orders for extracting these dependencies. The results show that each dependency is crucial for the performance of ART, especially for linear triage, which depends heavily on the detailed channel-level analysis. Moreover, modeling the dependencies in the sequence of channel to temporal to call as used in ART yields the best results, demonstrating the importance of the order in which these features are extracted. In conclusion, ART addresses the need for an elegant and efficient unified modeling approach for microservice incident management. It overcomes the complexity, interpretability, and scarcity challenges inherent in achieving unification through self-supervised learning, offering superior performance across all tasks. Our evaluation shows that ART significantly outperforms the existing methods in terms of anomaly detection, linear triage, and root cause localization, while also being more efficient. That's all. Thank you for your attention.